Particle accelerators do only one thing: they accelerate particles. Become of charged particles like electrons or protons are fed to them, and they speed them up and focus those particles using magnetic and electric field. This accelerated charge can fly through a vacuum in accelerators and nearly into speed of light until they crush into another beacon of charged particles or a fixed target. The resulting data obtained from such collision events can then help us understand more about the nature and behavior of subatomic particles. But a team from Stanford and SLAC is very first to have produced a functioning prototype of a miniature particle acceleration on a silicon chip. The research started on a nanoscale channel into their silicon chip and selected it in a vacuum just like a big accelerator. They accelerated electrons along this channel using infrared lasers plus with high pulse rate. The whole process takes place within a width of roughly 250 nanometers. Laser light consists of waves with the uniform period and amplitude. In infrared laser with a wavelength exactly twice the height of the channel is used. These light waves have electric fields that oscillate back and front. The green arrows indicate a positive electron force that can accelerate an electron, and red represents a retarding force. So to achieve net acceleration, the electrons must ensure more green arrows. The team achieved this by modifying the channel where they created a nanoscale pattern of ridges and gaps on the top and bottom of the channel. This structure increased the laser light electron field between the ridge and reduced it within the gap. Electrons traveling through the pattern channel now receive a big energy boost from the electron fields between the ridge and lose only a little energy as they pass through the smaller gap fields. The net resulted in a significant energy gain for those electrons that are perfectly timed with the laser light waves. It's true that the electrons were accelerated only to a fraction of speed that the big version gap up to, but no gap magnets or electric fields were required in this. This design required some brand new engineering on this team's part. They actually worked backward, starting with their end goal. So they ran inverse algorithms. This helped them come up with the layout of the non-scale structures with the chip that would let them achieve the goal. So although this prototype has not reached anything close to the acceleration we can achieve on those bigger versions, miniaturizing this tech could eventually have a big impact in medicine. One of the collaboration is even work on a development that would take these high energy electrons. Combining many of these chips together could provide hope to build entire fascinating accelerator in about the size of a box.